Hello everyone, I'm Sajedeh Faghih from Amirkabir University of Technology of Tehran. In this video, I want to talk about the security holes caused by hardware-level virtualization and introduce you to BluePill and SubVirt as real-world examples of these exploits. If you've seen the movie The Matrix, you might remember the scene where Neo, the main character who just realized he's inside the Matrix, is offered two pills, a blue pill and a red pill. He's told that if he takes the blue pill, he will stay in the Matrix, which represents ignorance in the movie. But if he takes the red pill, he escapes it. The blue pill malware gets its name from this exact concept, and the red pill is actually a technique used to detect this matrix. First, let's do a quick review of virtualization and how malware generally works, and then we'll dive deep into BluePill. What is virtualization? I like to call hardware-level virtualization hiding the truth from reality. The reality that virtual machines see is that they are the boss. They think they have full control over the system, but we know that's not true. They are just given virtualized hardware and resources, and the real boss is someone else. Who is that boss? The hypervisor, which sits in an abstraction layer below the operating system. The OSs sit in the layer above, meaning we can run multiple operating systems on a single physical machine. One of the main advantages of this is that OSs are strongly isolated, and if one crashes, the others continue running independently. Hypervisors also support features like live migration. However, this abstraction layer has also introduced new threats. How do traditional systems work? The OS was the absolute best. Okay, we only had 4 privilege levels, known as rings, from 0 to 3. The kernel resided in ring 0, but here is the catch. Antiviruses and firewalls also appear in ring 0. In the past, when hackers wanted to compromise a system, they would try to reach ring 0 to gain kernel level access. Once there, they could do whatever they wanted. However, since antiviruses were also in ring 0, they could detect and stop them. And malware had to be extremely powerful to hide and survive against all those security measures. To clarify, the antivirus software we see and interact with on our screens actually runs in ring 3. They scan our files against virus databases and handle heavy tasks. Why aren't these parts in ring 0? Because if they crash, we don't want the entire system to crash. But in ring 0, there are drivers that monitor application behaviors to ensure everything is safe and block malicious activities if necessary. Now, hardware-level virtualization has allowed us to have a hypervisor that is even more privileged than the OS. It operates in ring -1, making it completely invisible to the OS. But the big question, what if a malware gets into this ring and the OS can no longer see it? its benefits, virtualization has some drawbacks. It introduces significant overhead. It restricts us from fully utilizing all hardware advantages, and it creates brand new security threats because the OS cannot see the ring below it. Now, let's see how a malware exploits this feature. As I mentioned, malware used to target ring 0 to take control. Today, to reach ring -1, the malware still needs to get to ring 0 first to gain kernel privileges. This isn't easy, but since it doesn't execute its payload at this level, detection is incredibly hard for antiviruses. It might disguise itself using a valid signed application with a vulnerability on or trick us into clicking a corrupted file to gain that lower level access. Once it reaches the kernel level, it checks if the hardware supports virtualization technologies like VTX or SVM. At this point, the OS is still the boss. Next, the malware creates its own VMCs. It stands for Virtual Machine Control Structure. In the RAM, VMCs contains all information about the host operating systems. It has two main ports, the host state and the host state. The host state holds a snapshot of the host OS, while the host state contains the address of the hypervisor. The malware creates a VMCS, takes a snapshot of our actual physical system, and puts it in the host state. Then it places its own address in the host state. It enables VMX, executes the VM launch instruction, and literally moves our entire running system into a VM. Our system transitions into VMX non-root mode, and we don't even notice. From now on, whenever a VM exit occurs, the CPU looks at the host state and hands control over the malware, thinking it's a legitimate hypervisor. The malware is now the boss and can do whatever it wants without anyone noticing. Okay, now, what is BluePill? It's a concept that takes less than 3 lines of assembly code. It abuses hardware virtualization to move a running OS into a VM at runtime while I'm actively working with it, and I remain completely unaware. On the other hand, we have SubVirt. This was a research project by Microsoft to understand the true power of such malware. Unlike BluePill, SubVirt infects the hard drive's boot sector, specifically the MBR, stands for Master Boot Record. As a result, it takes control of the system during boot before the OS even loads and drops itself into ring -1. And this is the comparison that I mentioned. And let's see what can this malware actually do. Uh, Practically everything. For instance, it can manipulate memory. When we use HTTPS protocol, tools like Wireshark can't read the packet contents because they are encrypted. But this malware can, not by decrypting the data, but by reading the raw data directly from the memory before it even gets encrypted and sent over the network. It can also act as a keylogger, for example, monitoring every keystroke and stealing passwords effortlessly. Let me show you an example. I have booted up a VM. My VMware is the actual boss here, while my Windows 7 thinks it's in charge because it cannot see VMware. If we assume VMware is the malware, it can easily perform time manipulation. I'll suspend the VM. You can see the current time is 1:58 59 seconds, and when I resume the VM, you can see that the clock continues exactly from that time. It starts from 59 seconds. The OS didn't even notice the passage of time. Some suggest that a detection method is to set a maximum execution time for processes. If it takes longer, the OS assumes it's inside the VM. But as you can see, the malware can freeze or alter time, and the OS would be completely blind to it. Here is another demo. Since I can safely inject a ring-1 malware into my main OS to modify my physical RAM, I've created a simple simulation. I wrote a code that stores the number 123456 at a specific memory address, as you can see. Then I used Cheat Engine, a software mostly used in gaming to manipulate RAM, like for increasing health. So I select the target process, enter 123456, and let Cheat Engine find its address in the RAM. Then I add this to address list, see the address list, and manually change the value at that address. For example, this. The goal of this demo is to show how limited the user is and how they wouldn't even notice their system's memory being altered. Now, if I press enter in my terminal to recheck that number, you see that it's my number. Without any user request, the RAM was modified. But if I didn't change the number and press enter, you can see that it writes 123456 again. So, can we detect this malware? Most traditional methods are useless because at the end of the day, the malware is the boss. As I showed, time can easily be manipulated. Another method is using the CPUID instruction. The OS can request CPU information, which gets stored in registers like ECX register. The very first bit of ECX register indicates whether a system is running inside a VM. The OS could check this, but again, the malware can simply spoof this bit. Also, antiviruses could try to find the VMCS in the RAM, but the malware can hide that too. So, theoretically, we cannot detect these threats, and ultimately, the only real solution is to enforce strict system-level restrictions. For example, SecureBoot ensures that no unauthorized code can boot up, which effectively stops subvert. The other method is HVCI. It stands for Hypervisor Code Integrity. Based on my research, the approach Windows 10 and 11 use is essentially a counterattack. They literally run the main OS inside the VM themselves. This means there is already a legitimate Microsoft hypervisor running below. If a malware tries to enter that level, the hypervisor blocks it because the malware cannot easily replace an already running hypervisor. I didn't know this, and the first time I checked my CPUID, it told me my system was inside a VM, meaning I was inside the matrix, as you can see here. To disable this, I use this command and also turned off memory integrity. This feature ensures that only legally signed drivers can run at the kernel level. If I turn off the settings, I exit the matrix. Windows also uses VBS. It stands for Virtualization Based Security, which leverages hardware virtualization to create a small, highly isolated, and security memory enclave for sensitive data like passwords. Additionally, HVCI verifies any code before it runs in the kernel, preventing unauthorized code injection. So the irony is that OSs now use virtualization to defend hardware level virtualization security holes. Now, if I run that same script in my VM, it logically tells me that I'm inside the matrix, which is correct. Right now, Windows 7 is running inside the VM, and my Windows 11 is the boss. I can actually go into the VM's configuration file in Windows 11 and change it to force the CPUID bit to 0. This is my VM's configuration, and I will add this code. By adding this, I change CPUID to 0. Save this. Now, by restarting my virtual machine, if I run this again, as you see, Windows 7 will no longer detect that it's in a VM. This proves exactly how a malware can spoof this information. The holes. And for conclusion, we've learned that virtualization is a double-edged sword. Despite all its fantastic benefits, it can be extremely dangerous. All a malware needs to do is reach that lower level, and it can do whatever it wants without us ever finding out. That brings us to the end of this video. I hope you found it useful. Goodbye.